question I have for you is, you claim that diffraction-limited resolution and very high measurement speed can be achieved simultaneously. How is that possible?
Okay. For a diffraction-limited resolution, one has to work with collimated beam paths and diffraction-limited spots everywhere in the instrument. And for a high measurement speed, one needs a very high efficiency of all components in the instrument. The key features are single-mode coupled excitation lasers here, new technology photonic spectrometer fibers, and finally a highly efficient UHDS spectrometer.
Thank you very much. The next question I have is, David, with how many excitation sources and detectors can a WITec instrument be equipped?
To answer this question, we have to think about two different kind of configurations of the excitation sources. We have automated laser sources, which means lasers where the laser power can be adjusted, automated and stepless. Up to 4 of these laser sources can be connected to the instrument. In addition to that, an arbitrary number of laser sources with manual adjustment can be used. So short answer, motorized lasers 4, manual lasers an arbitrary number.
Fantastic, thank you. The next question I have is, at WITec instruments, how can I change the different operation modes, e.g. video to Raman?
Also for this question, we have to separate two different kinds of instruments. With a completely manual system, one has to switch 2 manual push rods for changing between Raman and video. For changing, for example, between Raman and AFM, it is just an objective turret that has to be rotated by one position. With an automated system, which is also available, everything is done automatically, which means just the measurement button has to be pressed in the software and everything is done automatically.
Thank you very much. The next question I have for you is, could you please tell us how deep can you go into the sample during a 3D scan of the sample? And does it depend on the nature of the sample? So whether it's a cell or a polymer or an inorganic material?
The short answer is basically the depth I can reach in the sample is only limited by the working distance of the objective. If the sample is transparent. If the sample is non-transparent, it is limited by the penetration depth of the excitation source in the sample. This is something which is depending on the sample itself and the excitation wavelength which is used. For instance, if a silicon sample is investigated, the penetration depth of 355 nanometers is far below 1 nanometer, 1 micrometer. If using 1064 nanometers, the penetration depth is much bigger than 10 micrometers. And this is the general answer on this question. It depends in the end of the transparency of the sample.
Lovely, thank you. The next question I have is, which of the techniques you presented can be used in liquids?
Using Raman imaging in liquids is absolutely no problem. And even the combination with true surface is possible, which means even rather inclined samples can be investigated in liquids while regarding the sample topography. Using an appropriate dipping objective, also combined Raman AFM measurements can be done, for example, in water.
Fantastic. The next question I have is there any additional equipment available to control environmental conditions, or is there free space to add my own device?
There are different configurations that can be mounted on the sample positioning stage. One example are cooling heating stages with or without vacuum. Another one is incubation chambers for defined temperature, humidity, and carbon dioxide concentrations. And yes, there are extensions to enable mounting also larger devices.
Fantastic, thank you very much. The next question is, do you also offer IR modules? Is this better or worse?
First question, yes, we offer IR modules. The question if it is better or worse, let's say it's depending on the question you have concerning the sample you want to investigate. IR compared to visible means that you tend to have lower fluorescence, which means if you have problems with fluorescence in the visible range, you can switch to IR excitation wavelengths. You also have a higher penetration depth, as I mentioned, concerning the 3D measurements. But in the end, it is depending on the sample and what's the goal.
Thank you, David. The next question I have is it possible to analyze ballpoint pen ink, laser toner, inkjet inks, and their intersections with a WITec Raman?
Yes and no. It is possible with a quite low resolution, and no imaging is possible. The reason is mainly the absorption of the samples, which means you get strong heating effects, which require quite low excitation powers and quite high integration times that are necessary. And this makes imaging impossible. But this is more or less a general property of the sample, and this is nothing system specific.
Thank you, that's really interesting. The next question is, how do you image biological samples with SEM?
I need a low vacuum, and a low acceleration voltage, and the sample should not be coated. Then it works.
Perfect. The next question is, how critical is the temperature oscillation for a long measurement?
This is basically a very good question, and the answer on that question is not easy. In general, if you look at the pure Raman instrument alone, it can be a problem. If you have a high resolution and you have high temperature changes, it might happen that the sample runs out of focus, which means the sample surface is not at the position of the microscope focus. However, we have some possibilities to level out these things. The first one is true surface itself. It works in a closed loop, which means it also reacts on drifts caused by temperature changes. The other one, there's also a software solution which helps to remove effects due to long time drifts, which means it is critical, but there are some ways to go around it, and currently it is no problem anymore to work with something like that.
Thank you very much, David, for that interesting answer. The next question I have is, in the true surface, the focus is obtained with the optical image, or is it obtained with the Raman signal?
Sorry, can you repeat?
Yes, of course. The question says, in the true surface, the focus is obtained with the optical image or with the Raman signal?
It is nothing of both. It is it is a separate technique. It's based on a signal of another laser, which is not in the visible range, and which does not affect the Raman signal. So, short answer is there's an additional laser, and the reflected signal is analyzed let's say to level out the distance between microscope objective and sample.
Thank you very much, David. That is all that we have time for today for the Q&A.